Welcome, everyone, today to this ABB Measurement and Analytics webinar entitled Everything You Need to Know About Mag Meters. Now, my name is Wayne, and I'm the technical host. So not the speaker. I'll introduce your host and speaker here shortly, but as the technical host, I just want to go over a couple of points with you, some housekeeping. First of all, during the webinar, you'll have access on your screen. There is a button called Q&A. This is where we'd like you to put in your questions. You can't speak today, but you will be able to type your questions throughout the webinar. We're going to reserve a good 15 minutes at the end of the webinar to have a session where we'll read these questions and answer those. Several days after this event, you'll also receive an email that has all of the questions, including those we don't get to, and their answers so that you can get the benefit of all of the questions that your colleagues have asked today and the expertise of our host. There is a chat feature. Don't use that for your questions, please, but it is a place that you can use if you're having a technical problem, something that you can chat with me about, and I can help you hopefully resolve that issue during the webinar. So those couple of things are what you need to know about your participation today. Let's move on to safety. Safety is an important issue for ABB, and they just want to remind you that if you're driving, please pull over for the duration of the webinar. If you're going to watch the screen, if you're just listening on your headset, great. But if you do want to fully watch and listen, maybe ask questions, please pull over. Same thing if you're walking, etc. We want you to be aware of your surroundings and be safe. Also, a nice reminder always for everyone to drink plenty of water, take a lot of breaks, stand up, and keep your body moving. All right, I've got one more slide to talk about is in the way of introduction. You're going to receive an email after this event. Now, this is providing you stay with us for the event, not necessarily the Q&A, but for those who stay for the full educational session, you're going to receive an email with a link to your professional certificate to show that you participated in this event. You also have an email related that shows you the slides and the recording of this webinar so that you can view it again if you'd like. Those who don't stay the entire time or register and didn't attend will get an email with the slides and the link to the webinar recorded version, but not a certificate. Okay, we're going to kick off the actual webinar now. So again, welcome to everything you need to know about mag meters. And I want to introduce our host, Mohit Manglani. He goes by Mo. Those of you who know him as Mo, is the water market leader for ABB Measurement Analytics. He's been serving in the municipal market for the past 15 years, very focused in the measurement and analytics space. So Mo, I'm going to turn the webinar over to you.
I appreciate it, Wayne. Thank you. Hey, everybody. Good morning, good afternoon, wherever you are in the U.S. I appreciate the time and your attention here today for the next 45 minutes or so. I also wanted to introduce on the side my colleague, Raghu Kumar, who's the America's Product Manager for Electromagnetic Flow Meters. Anything that gets a little beyond my capability, he's there to back me up and kind of give a little bit more in detail beyond what I can. So with that, as Wayne mentioned, I'm the water guy for ABB on the municipal market or the industrial water side. Anything that has to do with engineers, integrators, contractors, end users, specific municipalities, OEMs, etc. I'm there on the sales side, technically and commercially. Everything on ABB, anytime we do any kind of presentation, whether internal or external, we always start with safety and integrity. Wayne already covered the safety part. For the integrity, because I cover the municipal market, a big deal for our space is that ABB as a company, regardless of whatever division you're working with, whether it be drives, motors, DCS, obviously measurement for myself, we are not allowed to see commercially sensitive information, competitors' quotes, competitors' invoices, old invoices, if you rep them in the past. Basically, if it's, we're not allowed to see any pricing unless it's publicly on the website or online. We're not allowed to see any terms and conditions associated with anybody we compete against. commercially, and then obviously any information relating to intellectual property R&D type stuff. And this applies to ABB as a global company. So I just wanted to put it out there for those end users or customers out there. Again, we appreciate your business, and again, appreciate your time. I'm going to try my best not to bore you with slides. Please, this is for you. Anything I can be of value to help you in this space on the measurement side, whether it's flow, pressure, level, water analysis, whether it be lab grade or even process, please feel free to pass it by me. With that, mag meters. I'm going to go from basics to complicated. I'm going to try and cover everything from principles, as in what it is, how it works. We're going to go into applications, industrial and municipal. We're going to talk about best practices in terms of installation, mechanical and electrical. We're going to cover verification versus calibration, which comes up in the space as well. I tend to be a little bit more on the municipal side, so I'm going to focus a little bit heavier, more on there. So let's get into it. So mag meter, what is it? Mag meter is a spool piece. It's a flow meter. You mount it in line, and you're able to get a flow rate based off the process that's there. Obviously, there's a few things that are required to make it work. In terms of how it works on the principle of Faraday's law. The idea is that if I throw a conductive liquid through a magnetic field, I can generate a voltage, and that voltage is directly proportional to the flow. It's a very simple concept. Obviously, it's based on Faraday's law. Regardless of whether it's ABB's meter or anybody's mag meter, the concept is still the same in terms of basic functionality at the element level. In terms of what it looks like, I don't know if you guys can see my mouse, but basically it's a spool piece. It's a piece of pipe, typically Schedule 40 for most ANSI 150 applications. You got flanges on the side. You have coils on the top and the bottom that generate your magnetic field. You have metallic electrodes that capture that voltage. And usually on the inside of the line, you'll have a non-conductive material, whether it be rubber, Teflon, PFA, ceramic, etc. I want to go into all the materials. But the idea is that this is a basic mag meter of in terms of what it's made of and what it looks like on the inside. In terms of terminology, just to kind of go over details when somebody's talking to you or somebody's trying to explain something to you, or if you have questions. Process connection is always the connection that's touching mating piping. We have our outer flow tube, which is basically a housing. And again, I'm going to get into more detail there. You have a sensor coil housing that's on the outside that shields and protects all the electrical on the inside. You have a sensor head that's on the top of this device. Basically, all the analog measurements that are happening down here all come up into a board that's up in the top of the head. And this is what your transmitter is typically interfacing with. You have coils. These are basically coils that generate the magnetic field. You have electrodes. These are metallic items that are inside of the liner that capture the voltages that are being read when you run that conductive liquid through the magnetic field. This is your meter tube, like I said, the inside of the piping. And then in some cases, you'll have grounding electrodes, and the magnet coil are typically on 12 and 6 o'clock. So just to kind of give you a feel for how it's made and what goes into the making of a magnetic flow meter. The other consideration in terms of what this is, the only thing wetted, and because mag meters are a process device, they're touching your process, whether it be acid, basic, obviously it has to be liquid. The only thing wetted here is your liner and your electrodes. So anything you put inside your process, you need to make sure those two items that are touching your process are specified correctly for installation considerations. So just to kind of give you a feel of what a magnetic meter looks like on the inside, this basically shows you on the left-hand side, you'll see what the magnetic field looks like and how it's forming through the pipe here. And then on the right-hand side, you can actually see a cutaway of basically an ABB meter. You can see the coils at the 12 and the 6. You can see the coil and the electrodes on the side over here with all the wiring coming up to the top. So some people, they see these big tubes, they're measuring flow. Well, what's on the inside? This gives you a nice feel for what's in the inside. So for this one, I'm going to let Raghu comment on DC versus AC. Raghu, do you want to take lead?
Yep, thanks, Mo. Again, as Mo explained, that we have a magnetic field that has been generated. So this magnetic field is generated either by giving in an AC current or giving a DC current. Again, depending on the application, the choice of the excitation is decided. In case of an DC excitation, you choose it when you need a good low flow stability, a gooder accuracy. And when you choose an AC excitation, it is depending on the process. In sluggish, slurry kind of a process liquids, you would use the AC pulse excited flow meter versus a DC pulse excited flow meter.
Thank you. And then this is a picture of your AC magnet coil excitation. Basically, this is the type of power we're putting into the magnetic field such that you can get an accurate reading. I would say 95% of the meters out there we push into the market are DC powered, and they're more than capable in handling pretty much every application a normal mag meter can handle. AC meters we typically see in heavier slurries, heavier solids, heavier viscosities, or even super low conductivities. So that's kind of where the position is on deciding whether you want to go with a DC or an AC meter. So why mag meters for flow measurement? So you guys saw what the operating principle is. Obviously, it's a flow meter. It's an accurate device. The big kicker on mag meters, it's a full bore device. There are a lot of flow meters out there. There's no one perfect one for every application, unfortunately. Mag meters, they're full bore, so there's no pressure drop. In technologies like Vortex, Swirl, Coriolis, Venturi's, anything in line, you're going to have a pressure drop. You're paying for pressure, you're relying on gravity to give you pressure inside that line, and obviously you don't want the device to absorb all of it. So a mag meter is nice because it's a full bore device. I have a 10-inch line. I can put it in a 10-inch mag meter, depending on your velocity, more than likely it'll work very accurately. If you have changes in viscosity, if you have changes in density, even if you have temperature changes inside your line, inside your process, or even pressure changes, as long as it's within the operating capabilities of the flow tube itself, the Schedule 40 piping with the flanges, mag meter will work. 30-to-1 turn down on velocity. So like Raghu had mentioned, I can do high flows up to 33 feet per second. I can even go down to 1 feet per second. In terms of velocity, and I can still get an accurate reading. In terms of applications, and again, I'm going to go into more detail on the applications, but water is the big application. And even if you have a mix of water inside of chemicals, slurries, mixtures, pulp, basically anything that's conductive, mag meter will measure. It's got to be liquid, no gases. Partially filled pipes does not work. It has to be a liquid in that state. It has to be full pipe. So the idea, obviously, installation considerations are a requirement, and it has to be conductive because you need to generate that voltage to give you that flow signal. If your conductivity is too low, you might have issues getting that signal back accurately. So mag meter types and materials. So now we've talked about technology. We've talked about how it works, obviously the types. Now we're going to go into, well, what are they? What do they look like? A little more detail on it. So there's 3 mag meters. There's 3 types. One of them is, we call this a coil housing mag meter, clamp shell. I actually have a typo there. It's not clamp shell, it's clamp shell. We have something called a bean can, where basically you have a solid piece of pipe, and then you're able to obviously run flow through there as well. The nicer thing on the middle one here without the coil housing is that you can handle submergence better. In a lot of mag meter applications, especially in the municipal market, there are a lot of pumping stations. There's a lot of pumping stations. There's a lot of lift stations. There's a lot of outdoor installations that go underwater. You have basements that can get flooded. You have pits. So the idea is that you want to maintain submersion capability. You want to make sure it's rated for IP68 submersions. This clamshell housing, you can put it down underwater, down to 14 days, down to 16 feet continuously. With a coil housing where you don't have this clamshell design, you can put it underwater down to 30 feet and it'll last underwater forever, assuming you don't have any other events. And then the third type of meter is called an insertion probe. Imagine a 1-inch MPT process connection with a mag meter on the tip. We call this a mag on a stick. These are typically used to save money for larger lines. Obviously, a 60-inch mag meter that might will cost a lot more than a mag on a stick, and you can still maintain getting a flow indication. Mag meter accuracies on the inline sensors can go all the way down to 0.2% of actual flow rate, depending on the velocity. Insertion probes are typically 2% accuracy, depending on, assuming that it's installed the correct way. Nice thing about the insertion probe and the without the coil housing, again, they're both rated for continuous submersions, they're rated for variable, and they're rated down to 30 feet. But if you look at, depending on your application, again, a clamshell, it's lower cost, and most applications don't require the hefties that these guys have, whereas this guy meets most applications. Materials and electrodes. So I was mentioning in the beginning, right? The only thing touching your process, regardless of what it is, wastewater, potable water, sludge, or chemicals, or pulp and paper, whatever it might be, these are all your available, I would say not all, the majority of liners and electrodes that are out there. Hard rubber is probably your most common liner for simple applications. We use this a lot in the water market. You have soft rubber that can handle applications where you have bigger, thicker solids. They can bounce off the wall, which is kind of nice. You have Teflon. This is great for chemical applications, upstream and oil and gas applications. Thick Teflon, which is basically Teflon, but thicker, so it can handle higher temperatures. You have PFA, which is another type of Teflon. ETFE, which is the same as Teflon, except bonded. Linitex, which is a super soft rubber. And ceramic carbide for those super harsh solids applications, like in the cement market. In terms of electrode designs, again, 99% of the time, standard electrodes work just fine. Tungsten carbide, this is used primarily with the ceramic liner, where it has a substantial hardness. You have double layer for extra protection. You have pointed head in case you have an application where you have rags or pulp. You have a pointed head option where it will actually cut through the process if there's something that's coating, like I say, a standard electrode. And then we have our famous Swedish design shark fin electrode, which obviously, if you look at the pointed head, which is the Swedish is a bit more expensive, limited in terms of materials of what you can get, but essentially you can cut up your process even better. So I would say if you're looking to specify mags or use them, in the water market, hard rubber is probably your go-to, and then in the industrial market, Teflon is probably your go-to. In most cases, again, everything is application specific. Best practices. So, in the space I come into, there's people that have many, obviously, different experiences in the space, whether it be on the industrial market or the municipal market. So I wanted to kind of go over what is best practice. If you're an engineer specifying, these are things you want to consider to apply in your specification. If you're an end user, you're having issues with the mag meter you have out there. Mag meters have been, just to circle back, mag meters have been around for a long time. And there are still flow tubes out there that are 50, 60 years old that are still working. The electronics have actually bypassed the life of the electronics over the flow tube. So these best practices, if you're having troubles out in the field, these are some things that you can look at, maybe improving the performance or improving the accuracy of what you have. So, like I said, a mag meter needs three things: liquid, conductive, and full pipe. Liquid's usually easy because usually water is attached to the application, or some kind of, obviously, liquid base, whether it be a chemical or water. Conductive is usually another consideration. Obviously, most people that are working with mag meters, they're not running a super basic application through the line. The hardest one, I would say, is ensuring that you have a full pipe. A mag meter is a velocity device. If there's air in the pipe, it will seed it and it may register it as the wrong flow. Or if the mag meter is smart enough, it'll be able to tell you that, hey, something's wrong inside your process, which I might add, ABB obviously has that capability. First thing is, on an installation, your best installation is a vertical up. You're going against gravity. The nice thing is, you're always guaranteed a full pipe when you have enough pressure going through the line. If you install it on the top of an elbow, that's a little bit of a challenge because then your line can drain and you may not know if you have a full pipe or not. So this is not recommended, but if you have an installation where you're coming down and then going back up, you'll always have enough back pressure to have a full pipe. So this is, like I said, for those that have met me or if I've done a presentation for you before, you may have seen this slide. So if you look at this meter over here, if you have flow coming down all the way on the left over here, the risk of this installation is there's no guarantee that you're going to have a full pipe. That mag meter might give you issues or a noisy output. If you're right around a bend, you need a specialized mag meter, a 0x0 mag meter, which Allied ABB does have. The best installation, as mentioned before, is a vertical up. You're going against gravity. You're always guaranteed a full pipe. And then obviously, if you're going on a top of a bend, as long as you have enough upstream and downstream piping, you'll be able to accommodate good accuracy for the meter itself. So I've had some customers that have installed stuff under the ground and they have a diagonal in their piping. The best way that you want to put a mag meter into this installation is flow going up on the diagonal. It's always recommended to have a siphon or an air relief valve at the topmost part of the valve, on the topmost part of the pipe, such that if there is air building up in here, it has a place to go because you don't want the air to be inside the mag meter. Again, Faraday's law is on the principle of liquid, 100%. Horizontal position. So obviously, depending on your installation, whether you're inside the fence or outside the fence of your facility, if it's always saying if you're doing a horizontal installation, try to give it a 3 degree and not to exceed a 3 degree up on the piping. The reason we say that is because if there is air or air bubbles in the line or entrained air inside the liquid, depending on your application, you want it to get free. So having that little bit of an incline, it's not recommended to go fully horizontal. It's always recommended to have a slight incline. This is kind of where I see the biggest challenges coming of installations and specifications. Degassing is very important. Again, got to avoid air or any kind of gas inside the line. Control valves. So a mag meter, what's it used for? It's used for control. It's used for operation. It might be used for batch filling. It might be used, it's used for all kinds of operations because it's a 0.2% device. It's an indication for you to make decisions inside your facility or outside your facility. Installing it, obviously in a manufacturer's recommendations, we have our 0x0 meter. We have our standard 3x2 meter. Control valves obviously cause disturbances in the flow. A mag meter likes laminar flow. It likes consistent, heterogeneous conductivity process going through it so that it can give you an accurate reading. The problem is if you introduce a butterfly valve upstream, if you install a half-closed gate valve or a knife valve, the risk of it is that's going to cause turbulence, which is either going to cause one, an inaccuracy in your mag meter reading, or two, it's going to cause a noisy output. And like I said, most people buy the mag meter because they want flow, they want to be able to make accurate decisions or bill properly, and they need to make sure it's accurate. Noisy output, obviously that's far from accurate. So the idea is that if you're installing downstream from a valve, we always recommend 2 piping. The idea is that if this valve is moving in any capacity, you don't want any of the flow to end up back in here. 2 is a safe number for most manufacturers. If you have a control valve upstream, it's a butterfly valve. Butterfly valve is the one that's the hardest. That, because you already have a valve in the middle of the piping, that's automatically going to cause a disturbance in your laminar flow. So we always say for a butterfly valve, give us 10 upstream. But if you have gate valves that are always open, unless you have to isolate something, you can put that up right next to the valve because most of the time those are fully open, full bore valves. So just keep in mind the installation conditions of whatever's upstream and downstream of the meter. You can only imagine, based on how much data I've given you so far, troubleshooting these things when they're incorrectly specified comes to be a little bit of a challenge because these are all considerations in making sure it's a successful installation. Concentric tapers. Another, you can put reducers right next to the mag meter. Most people, a mag meter, I had mentioned earlier, if I have a 10-inch pipe, I can typically install a 10-inch valve, 10-inch mag meter, and I'll get good accuracy. the challenge becomes if the velocity inside the piping, due to increased viscosity, due to increased conditions of the process, you might need to go to a smaller mag meter to get increased velocity to get the accuracies you need. So the idea is that if you want to install a concentric taper on the upstream and downstream of the mag meter, this is perfectly acceptable. Concentric tapers, they have to be mounted directly onto the flanges. Obviously, you can have rings on the inside of there, and then you want to make sure that the taper angle is less than 8 degrees per side. Pressure loss obviously is minimal, and it will be determined by whomever you source your concentric tapers from. So I just wanted to kind of show you what this looked like and what it is. So installations around bends, this comes up a lot. Mo, I don't have any upstream diameters. I need to install the meter right next to a bend. You can look in this picture. This shows the velocity profile of what flow looks like coming around a bend. You can see that's far from a laminar. The nice thing is we do have a 0x0 meter. It's a reduced bore meter such that we can flatten the profile and give it the mag meter the laminar flow to give you the accuracy and guarantee you can install the mag meter right around the bend. If you're working on a greenfield project, new application, new installation, again, best practice is always three piping diameters upstream. This is just to kind of show, again, this is the idea of this is to show you that if I install around a bend, this is my flow profile here, the 0.25 PD piping diameters. But if I have 5, you can see I have perfectly laminar flow. So this is a nice representation of what good piping looks like and how it involves your flow profile. Grounding. So a mag meter, the coils are generating a magnetic field. The magnetic field is prone to disturbance, period. The other thing in mag meters is that typically they might be using the same power panel as a drive, a motor, a bigger device, a 480 volt power supply. So the idea is that a mag meter is a very low power device. So it's going to pick up noise. Obviously, if you're using this for control, operation, or billing, you want to minimize noise as much as possible. So we did an analysis to validate if I ground the device or cross-bond the device, obviously I have a much more stable signal and I have a much better accuracy. If I don't have a ground or a cross-bond, you can see noise picking up depending on situations that are happening in the field. Improper grounding or cross-bonding is by far one of the leading causes of mag meter degradation or performance. It will cause you to have issues in your accuracy. As I mentioned, this is a 0.2% device. So, and on top of that, when you're doing control, obviously you want a stable output signal. So again, bonding and cross bonding helps maintain that stable signal. You want to make sure it's isolated from other heavier electrical equipment. And grounding is just good practice in general for any large electrical devices that you have. So what does good ground look like? What does good cross bonding look like? So in ABB's world, there's 3 ways. You have protection rings, you have grounding rings, and you have grounding electrodes. Number 1, we love protection rings. Protection rings are a way that you can actually mount the ring directly onto the flange of the meter. We typically do this for Teflon units because we want to protect the liner, because Teflon naturally wants to come straight. The ring holds it back right next to the flange, and we'll tap the flange for you and secure it in place. And on top of that, we'll give you a little tab over here that allows you to cross bond to the flange, to the mag meter. Number 2, for liners like hard rubber, we'll give you a wafer ring. You can sandwich it between your mag meter flange and your mating flange. This is exactly where they go. So imagine your mating flange. You'll have a gasket, ring, gasket, mag meter, gasket, ring, gasket, mag meter, or sorry, mating flange. So the consideration of a grounding ring, the inconvenience of it is it does add to the overall length of the meter flow tube. And so you have to accommodate that in your calculations. But the nice thing is it'll give you that nice stable output. The other way to accommodate grounding is using a grounding electrode. So as I mentioned, a mag meter has 2 electrodes, typically at 3 o'clock and 9 o'clock. That's absorbing that voltage, right, to give you that flow reading. There's another electrode that we have that goes at the 6 o'clock that'll connect it directly to a ground. The grounding electrode, it's not that great, because if you have an application which has a little bit of solids in it, over time, solids will settle on the bottom of the meter at 6 o'clock. So it'll eventually coat the electrode, the grounding electrode. The other thing is grounding electrodes, they're tiny. If you look at the surface area of the grounding ring, you're covering your entire line on the upstream and downstream side. A grounding electrode is the little piece of metal at the bottom of the liner. It's not as effective, and typically in ABB's world, we always recommend grounding rings or protection rings in every installation. Because the last thing you want is you didn't install the ring and you got to install it after the fact. So just to show you a picture of what good cross bonding looks like. So like I said, mag meter lines, they're typically installed on metallic lines or PVC lines, which are not conductive. If you have iron metal lines, you want to make sure the potential of whatever noise is there is at the same potential of the process. The way to do this is, I have a grounding ring, mag meter flange to the ring on both sides, mating flange to the ring, and then having a connection between the mating flange and the mating flange. Even if you have a surge strike or an event or a surge of power in your power supply, or anything that happens on the line or in your process, the idea is this kind of apparatus, we call this a floating ground, it gets rid of noise and it bypasses the mag meter to prevent any disturbances in your accuracy. So the idea is this is what good looks like on the cross bonding side. And we typically say apply this to every mag meter we sell, whether it be any of ABB's or even we would say to our competitors. Just so you can see what we do and how we test it on the rig. So obviously, when ABB or when any manufacturer builds a mag meter, we test it in lab conditions. We're inside of a clean area, we have clean water, perfect process. When we make mag meters, we give you an accuracy based on ideal conditions. Obviously, in the field, you're far from ideal. It might be power supply, it might be cross bonding, it might be other electrical disturbances. The idea is that you want to make sure the installation at which we test and calibrate to matches it as close as possible to the field. Verification versus calibration. So great conversation. So you specified a mag meter, everything's working. You might be using it for billing purposes, whatever it might be. Somebody challenges you and said, well, prove to me that device is accurate, right? So mag meters, we already use it for operations. We use it for controls. We use it for chemical dosing. We use it to determine what we need to do to our process, whether it's controlling a valve, controlling chemicals, whatever it might be, filling or batching, right? Verification, what it is, it's the capability to match the health of the device and correlate it directly to the accuracy. So I'll say this, back in the day, if somebody said, I need to calibrate a mag meter, what they had to do was they had to shut down production or the line or isolate it, whatever it might be. They had to remove the meter out of the line. They had to send it back to a facility that builds mag meters or does calibrations. You'd have to run known flow through it. Obviously, you get a calibration certificate. That's your calibration to make sure that the meter is accurate. Obviously, that's a lot of downtime because you have to have a spare. You have to have downtime to take out the mag meter or use a bypass. Obviously, there's time associated with being down and getting back up electrically, mechanically, etc. We offer the capability such that you can connect a device on the outside of our, this is specific to ABB, on the outside of our device, such that we can test the device to the standards in which we manufactured the device. And then assuming that's within certain tolerances that we've set, you can get a nice certificate that says, hey, this thing is accurate, it works, and it's healthy. Within that same tool, you're able to predict predictive maintenance if you have degradation that's coming over time. This is called verification. This is not calibration. Verification is not a calibration. So I've heard of a lot of end users or customers say, can you come out here and calibrate my dice? Not possible. Calibration has to happen in a known flow facility. Verification are what most people are doing out in the field today. This verification is the capability, and you can do it all in the field while your process is running. There's limited downtime unless you're testing the outputs. So just to share that out there. If you look at calibration versus verification, calibration takes a lot more time and it adds to the cost of ownership. Verification, like I apologize, it says ABB ability. Automatic maintenance, one tool, one software, one piece of hardware. You can plan for downtime if you need it. And if you do have a situation or you need to validate the health of the device, you can do it on demand. So with that, that's mag meters in a nutshell. I hope I've covered the majority of what people are looking for. We're going to go into a little bit of an application side. In my market, obviously the water market, mag meters are used in almost every step of the process, because before something goes into a process and after something comes into a process, you need indication of what's happened to the flow, whether you're dosing, whether you're using totalized value, whether you're putting it into storage, so you know how much you have in your tank or vessel, whether you're using it in potable water distribution or wholesale potable water management. You need to know what's going through your line. And you need to either bill accordingly, you need to make sure that water is not being lost or leaked somewhere. The idea is that this is where mag meters spend their best times. Raw water abstraction, right? Coming directly from a source water body, might be a river, might be a lake, might be a sea, might be a reservoir. Wells, obviously in the north, I would say more than the south, we have a lot of water wells. Obviously in the south, I would say you have it too. Desalination plant effluent, right, on the outside. Sedimentation and filtration, raw water treatment, again for chemical dosing. Sludge thickening, like I said, mags can handle sludge applications and higher solid applications. Potable water storage, to know what you obviously have saved up for your town or city. Pumping stations, lift stations, and industrial water. So in most industrial facilities that have a water plant, typically it's a requirement either of EPA or some kind of permit that you have to monitor pH, turbidity, and flow. And then the idea is that on that discharge, to make sure you're not putting too much in based on what the EPA defines in your permit, you would have to verify the device. On the wastewater side, again, all these are applications where mag meters can measure outside the air compressor, obviously. RAS, WAS, grid disposable, bar screens, if you're having raw sewage come through, aeration tanks going in and out, secondary clarifiers, activated sludge, chemicals, dosing associated with the wastewater process, aeration, digestion, sludge conditioning. Again, mag meter lives in all of these spaces. So again, the idea is that you want to make sure you apply best practices with any of the applications you might come across. So just to show you some pretty pictures, pumping stations and lift stations are one of the core applications out in the field that we come across. Things to consider, right? Make sure the installation piping, there's plenty available based on the mag meter that's being specified. Make sure you're putting it in an orientation such that the pipe is always full. You have to make sure, obviously, if it's out in the field, you also have to make sure that it's, if it's going to be, can get put underwater, you don't want to specify an IP67 rated meter. You want to make sure it's IP68 rated for the amount of water that's going to be on top of it. Validate if you want to put it inside of a vault, which is good practice, or whether it's buried underground under rock and dirt. That coil housing I was showing you in the beginning, that's not rated for buriable. You have to go with the bean can design. You have to make sure the liner electrodes are based on the wastewater composition that you have. You want to make sure you have clean, dedicated power. Obviously, if you're out in the field and there's not clean power available, that might be challenges for your installation. And obviously, cross bonding and grounding. You want to make sure that those practices are applied to get the best accurate meter you can get. Sludge tanks. Again, I'm covering the municipal side. Custody transfer tanks, tanks coming in, tanks coming out. Mag meters, all of them have totalizers built into them for the most part. So if you want to make sure you know what's going into a vessel or a tank or through a station, you have a totalizer built onto the device. Influent and effluent. I love this picture. My influent's the smaller tank over here with after a chemical and going through the process, it's coming back out in a bigger meter. because obviously more stuff is being applied to it. But people use it for water balancing across in the distribution networks or even inside a facility to make sure that there's no leaks or anything there. Leachate tanks, not the prettiest applications, not the best smelling application, but great application for a mag meter. Teflon liner, typically Hassel IC or platinum electrodes to hold up against the process itself. Raw water wells for source water. If you're pumping water out of the ground with a nice pump, obviously you to validate and check that pump, you have your pressure gauge on your pump to validate the flow curve is operating efficiently. Mag meter is a tool to verify that pump. Industrial applications. So mag meters play pretty much in every market. Chemical and petrochem, upstream oil and gas, transportation, food and beverage for milk, cheese, etc. Power energy, thinking cooling towers, pulp and paper, paper applications for pulp and paper facilities, cement and mining for the mines, and then metals and steel for steel plants. So in typical chemical plant applications, you'll see acid flows. Oh, one thing I might add. If you're running a mag meter and you are injecting chemicals inside of it, and the reason that this acid flow came up, a mag meter should, like I said, the mag meter conductivity wise has to be heterogeneous. If you have a chemical feed line coming in upstream of the mag meter, when you stream in chemicals into a water or some application, you have superconductivity running through that line. That will throw a mag meter's output, drive it crazy. If you're doing chemical injection into a process line and a mag meter's there, you want to make sure that injection is downstream of the meter, not upstream of the meter. I wanted to add that because I saw the acid flow here. It just came to mind. Acid flows, sodium hypo, sodium hypochlorite, chlorine, bleach, you name it. Solvent flows, polymers. Big thing with polymers is you want to make sure that they have conductivity. You think of paint. Paint is not the best application for a mag meter because number one, it coats. Number two, it may not be conductive. Process water and wastewater processing, obviously on the industrial water side for chemical plants. Oil and gas applications, obviously on a separator, probably have oil going one way. You'll have the water that's being fractured out going another way. Typically in our space, we see mag meters on the water side, and on the oil side, we'll see Coriolis meters. Another technology, just to kind of give an example. You'll see chemical feed in upstream oil and gas. Obviously, you'll see water flows. You'll see pre-treatment at the wells and post-treatment, and obviously wastewater processing as well. Food and beverage facilities, again, massive market for mag meters as well as Coriolis meters. Processed water, big deal for measuring accurately for control purposes. Milk soda processing, which have plenty of conductivity. Beer brewing, distilling spirits, plenty of conductivity again, and wastewater processing. Power plant applications, again, cooling towers, etc. Water flow to the boilers. Boilers obviously have to keep cool. We've even installed mag meters in nuclear facilities, taking care of that cooling water. Pulp and paper facilities, you guys have seen, for those of you on the pulp and paper side, you've seen pulp and paper machines, dye injection, chemical injection, pulp flows with a little bit of stock in it, plain coating flows, and wet cement applications. And timing, I'm running a little short, so I'm going to run it a little bit faster. With that, I wanted to leave a good 15 minutes for Q&A. So Raghu, I'm going to ask you to come off mute and be glad to take any questions.
All right. This is your technical host again. I'm going to tee up the questions for you guys. And thanks, Mo, for a great presentation, Raghu. So we have Amelia asking about what about use on a 60-inch water line that has 30% internal sedimentation? Could the flow still somewhat be accurately determined?
Raghu, do you want to take a shot on that?
Yeah. Okay. So if there is a sedimentation inside the the flow meter tube itself, then yeah, the accuracy would not be that great. Again, if you're expecting a 0.2% accuracy or a 0.4% accuracy on a 30% sedimentation, it's not possible if it's sedimented into the flow meter. But if it's down upstream or downstream across the pipeline, then it's not a problem. So the place where the measurement is happening, if that's 30% of sedimentation there, then that's not, yeah, you cannot get good accuracy.
All right, great. Razard asked, does the meter need an extra grounding rod?
So, it's funny. We actually don't recommend grounding rods. Our form of grounding is actually cross bonding, where we make the potential of the line equal with the potential of the process, because you don't want imbalanced electrodes or coils such that you get inaccuracies on the line. So it would not need an extra grounding rod. Raghu, do you want to comment further?
No, I totally agree to what you said, Mo, that we don't need a separate grounding rod. As Mo showed in the slides, we need a cross bonding, which means we maintain the potential across the pipe as same. So we don't need that.
Got it.
All right, excellent. That actually took care of, there were 2 or 3 questions related to grounding and bonding, so you knocked those out. Bob asked, how does tuberculation affect the accuracy of the mag meter?
Raghu, I'm not gonna lie, that wasn't a SAT word, so I don't know.
To be honest, I'm not sure about.
Probably means turbidity, but again, the person, Bob, if you want to clarify, you can retype that. But he may mean turbidity, perhaps.
Okay. If it does mean turbidity, again, liquid conductive full pipe. Even if there's turbidity in the water, if there's sludge in the water, there's wastewater in the water, there's even mixed chemicals inside the water. Turbidity is not a big deal inside of mag meters, as long as the viscosity of that turbidity doesn't affect the overall mixture to exceed a certain amount. So I hope that covers it, Raghu.
That's right. Yep.
Okay, you guys are doing great. I appreciate that. Another one, someone's asking about how accuracy may be affected at low flow and they said battery powered mag meters, but for your mag meter, the one you're describing.
Oh, no. So ABB does do battery. We do solar powered. We do AC powered. We do DC powered. We do every kind of power you can imagine. So I'm going to let Raghu comment on that one because that's his favorite meter.
Okay. So the accuracy at low flow for a battery powered mag meters is typically, I would say, not good as AC powered. That's because you do not have enough current to drive the coil, so it's not good. But again, it depends on what is low flow. If you are speaking about few feet per second, that's not a problem. But if you are speaking about, let's say, again, if I use a metric system, if you're speaking about millimeters per second, then then the accuracy is not bad. It's in the range of, let's say, 3 to 5%. It's not 30 or 40%. It's in the range of 3 to 5% when you compare to a 0.2 or a 0.4%, as Mo was mentioning. So if you're still okay with 3 to 5%, then battery powered mags are good in the low flow conditions as well.
Yeah, so I additionally might add battery powered meters. Like Raghu mentioned, you have better noise suppression in AC or DC meters. When you have battery powered meters, I typically don't have people use that for indication. They'll use even that for billing meters. Typically, I kind of push for higher velocity is always better. And on our low flow battery powered meters, we offer that reduced bore meter, which actually handles low flows better. And it does have a certification on it, and it's called OIML, such that you can get great accuracy at low flows compared to our competition. So I just wanted to kind of add that as well, to say that we do have some points that cover our lack of noise suppression to make the meter a better meter on the battery side.
I want to thank our guests for giving us a little clarification on tuberculation, which we debated a minute ago, is a buildup of corrosion or rust in pipes. So how would that affect your answer?
Got it. So, Raghu, do you want to comment or do you want me to?
Yep, go ahead, go ahead.
So if there's rust buildup on the inside of pipes, so a mag meter, as mentioned, you have two wetted materials. You have the electrodes and the liner.
Line.
You want to make sure if there's a chance that your line could be rusting on the inside. Hopefully, as a process engineer, you would know what's going on inside of your line. If there's a chance, number one, it has to be non-magnetic, otherwise it'll directly affect the performance and accuracy of the meter. Number two, if there is a chance that rust could be in your line, you want to make sure that the liner that you choose and the electrodes that you choose might be maybe a little bit harder on the electrodes. Instead of stainless, might go Hastelloy or titanium. Instead of going for maybe a Teflon liner, or you might go to a hard rubber that can handle abrasives better in case that could happen. So you just want to make sure that the materials specified inside are proper and associated properly for tubucation if that could occur.
Excellent. An interesting question here. Does the calibration of the mag meter drift over time? And is that drift evident during verification?
Raghu?
Yep. So a typical mag meter doesn't drift over time. Again, when we speak over time, if you're speaking about, let's say, 10 years or 15 years, yes, then the electronics degraded and there's that. But you don't see a typical drift happening in a year or two. The drift is not so evident in a year or two, but over 10, 15 years, you could probably see a small drift, and that's when you recalibrate it. And when you look at verification versus calibration, very specific onto the drift part, in the shorter lifespan of the product, in, let's say, after using a new product for the first 1 year, 2 years, 3 years, the performance of the meter is dependent on certain aspects of the meter itself, the coil, the electrode, which Mo explained, the construction. And this verification helps you to verify those parts to ensure that the accuracy is achieved.
Yeah. So you would notice it if there was a problem.
Yep.
And you run a verification after 15 years and the meter still passes, then you can be assured that your accuracy is still maintained. But if something happens or event occurs or something's changed, substantial resistances or inductance, whatever it might be in the meter itself, you will be able to see that in the verification, because then it won't be within the tolerance in which we can guarantee the accuracy. So the verification will help identify it. And then in our verification tool, we do offer the capability, if you have the same critical meter over and over and it's being verified every quarter or every year, whatever it might be, whatever frequency, you can look at those reports side by side and we can analyze that data to tell you, hey, the electrodes are starting to disappear over here. Still within accuracy, but you might want to look in the long-term maintenance to say, get this replaced. So you will be able to tell that kind of detail, that level of detail and analysis inside those verifications.
Excellent. And I just commend our audience on so many great questions, and they're still flowing in. And again, I want to remind you, we're not going to get to them all. We're going to do a few more, but you will receive an email. It'll be several days later where we're going to answer all of the questions. You'll be able to see all that were asked and the answers. Here's a couple more. Interesting. Have you ever buried your mag meter? And if so, do you have any standard, I don't know, do you have a drawing, something as a guide for burying mag meters underground?
So there's two answers to that question. So number one, yes, we can bury our mag meters. Yes, we do have versions of our mag meter that you have to specify that inline sensor, not the clamshell version, the bean cam version, because that's the only type of meter that'll handle all the weight of everything you're trying to put on top of it. In terms of having a proper picture of what good looks like, absolutely, we can send that to you. We'll put it, when we send the follow-up questions, we'll make sure to add that to that response so you can see what that picture should look like.
Here's another very specific application question. Any test data available for electric arc furnace water cooling applications, given the high magnetic interference from the high current arc furnace? So maybe just that application in general.
I believe, again, there is, So again, the flow meters are always tested for all magnetic interferences like EMI, EMCs, and there are certain standards that are driven to test the product so that we could put it into the market. So we have all of them, but there is no specific test that is being done for, let's say, electric magnetic arc interface, unless the magnetic interference from this specific application is too high compared to a general product. And that specific question I probably cannot answer at this point of time. Probably we can look at it and we can reply them later.
Excellent. And back to the buried one for just a second. Somebody kind of threw a different wrinkle. How about submersion, say up to 10 feet?
So regardless of the body design on ABB meters, all of our meters minimal are rated down to 16.5 feet for 14 days. Standard IP68 submersion specification underwater. It's the variable one that actually gives you more capability, more depth, and prolonged submersion. So IP68 standard is a standard across all of our meters. The other thing I might add, obviously our mag meters are not just a flow tube, it's also a transmitter as well. To get that IP68 submersion, you would have to make sure you go with the remote electronics. So I just wanted to put that out there. I hope that answers that question.
All right. I think we have time for two more. Another kind of an application, very specific application, but others might benefit from this that our colleague Jim asked. That we have mag meters on our water wells which drain back when the well pump is off. So in other words, sometimes the mag meter is dry. Is the reading during the pumping cycle going to be accurate, or will the dry period cause some types of inaccuracy?
Oh, good. You want to take a stab at that?
Okay. So the mag meters do measure either the forward or the reverse. So we call a forward totalizer and a reverse totalizer. So the velocity and the totalizer you have all the variants. So you have a forward, which is during the pumping, you measure that. The velocity is there, the totalizer gets updated. When during drain, if the water goes back to the well, that's also measured and recorded. It's available. And in case if you want to use it for billing application, you have the net. So difference between the forward and the reverse is also available. But when it comes to an accuracy for the draining part, it depends on the installation. If the installation is on a free flow direction, then the pipe is probably not full, and then the measurement would not be accurate. And if such an application is there, we need to look at a place where we install the mag meter that both the forward and the reverse are measured accurately. So it's just following the right installation practice to get the right accuracy either in the forward and the reverse direction. But as a mag meter, both forward and reverse measurements are accurately same.
All right, last one. There's probably 15 questions left, but we'll just do one more, and then you'll receive all of these later. From David, how far upstream can you inject your product, the mag meter, without significantly affecting connectivity?
So I'll give you some field experience from that one. I've seen chemical feed be directly upstream of the meter, where it directly, obviously, affects the mag meter output. I've seen it be as much as 30 feet away, where you just have straight pipe, a chemical feed is coming in without any bends or any kind of mixing happening. And 50 feet away, even though it's plenty of upstream and everything, I've seen it affect the mag meter's output. As soon as you dose water, it works just fine. So it really comes down to how well that chemical is mixed before it reaches that mag meter to know how it would affect it. Unfortunately, there's no direct guide to say this is best practice. It's more of a, depends on how the feed is, and depending, I would say if you have to install say a chem feed upstream, make it as far up as you can and make sure you have a mixer in there to make it heterogeneous so that the mag meter sees consistency. The only thing to note, I would say, you would probably also have to increase damping in the mag meter to make sure you offset that bump in the flow reading itself. Raghu, do you have any additional comments there?
No, that's
excellent. All right, well, that's the end of our hour. I'm going to turn it back over to you, Mo, for any final thoughts. I think you have a last slide there, and you can sign off at the end, and I will close the webinar.
Absolutely. So everybody that attended the call, truly appreciate your time. Thank you very much for attending. There's a lot of great questions over here. I still see we have more than 20 open. Raghu and I will work diligently to get that done as soon as possible so you guys can see the responses to everything. Another thing I had, as I mentioned, I'm on the water side, on the municipal side. WEFTEC is coming up in New Orleans, October 7th or 9th. If you want to come and meet me, be glad to meet you. Where ABB is going to be in booth 4129, WEFTEC, WEFTEC. Look forward to meeting you and be glad hopefully we can answer all your questions. Within the responses as well, I think it will be my contact information will be there as well as my team. And we can follow more diligently as well. And again, as Wayne mentioned, PDH certificates, PDHs are available. Just stick on for a little bit more and please answer the survey we have at the end if you can. Thank you. Have a great